Hi everybody, let's quickly revisit the very technique which was used to get to the solution of a non-homogeneous system of n linear equations in n unknowns, and then as I promised you, we would be demonstrating that particular technique to actually learn how to practically compute the solution for a non-homogeneous system of n linear equations in n unknowns. So what was the concept related to finding the solution of any non-homogeneous system of n linear equations in n unknowns? What was the technique? The technique first of all was that whenever you have any non-homogeneous system of n linear equations in n unknowns, that particular system can always be expressed as Ax equals B, where A is an n cross n square matrix. So your A is n cross n square matrix. This is the matrix which plays the entire role in concluding about this nature of the solution of a non-homogeneous system. Why? Because the moment you have converted the given system into this matrix equation form, you need to just talk about the determinant of A. The moment A has come out to be an n cross n square matrix known as the coefficient matrix, what is it called? It is called the coefficient matrix. You know why is it called the coefficient matrix? And this matrix is a square matrix. So in here, with respect to this square matrix, we compute the determinant. This determinant can either come out to be not equal to 0 or can come out to be equal to 0. Coming out to be not equal to 0 means A is non-singular. A is non-singular, and this means A is singular matrix. A is non-singular means A inverse exists. A is singular means A inverse does not exist. Here what did we derive as the conclusion? The moment you are getting that A is non-singular, that means Ax equals B has a unique solution. Ax equals B has a unique solution given by capital X equals A inverse B, because in this case inverse definitely exists. A inverse exists because A is non-singular, and therefore when you multiply that A inverse with the given matrix B in here, you get your very solution, which is the only solution for the system. There is no other solution for the system. Here we said that if the system has at least one solution, it is consistent. This system, in this case when its coefficient matrix is non-singular, is definitely a consistent system. Why? Because it has not just at least one solution, it has exactly one solution. That type of consistency prevails over here in this context. After that, if suppose the determinant is equal to 0, that means A is singular, then the conclusions are two. There are two conclusions. Either the system has no solution or it has infinitely many solutions. When do you say that it has no solution? I say it has no solution when the matrix adjoint of A into B turns out to be not a null matrix of order n cross 1. And I say there are infinitely many solutions when adjoint of A into B turns out to be equal to null matrix of order n cross 1. In here, why are we bringing in the context of adjoint and not inverse? Because in here when A is singular, A inverse does not exist. So how can you even talk about computing A inverse and then multiplying it with B and then talking about the answer? So here A inverse does not get multiplied with B. Here adjoint of A multiplies with B. If this comes out to be equal to null matrix, then declare that there are infinitely many solutions. If it comes out to be not equal to the null matrix of order n cross 1, declare that the system has no solution. In this case it is inconsistent, here it is consistent, here it is consistent. Clear? This is consistent because it has not just at least one solution, but actually it has infinitely many solutions. Here it is consistent because here it does not have at least one solution, here it has exactly one solution, and this is inconsistent because in here it has absolutely no solution, and I need at least one solution for the system to be able to call it a consistent system. Now, how to actually demonstrate the working of this entire process? Let us look at these questions that we have on the board. The first question is, the system is given to us and the system is concerning two linear equations in two unknowns x and y, and also you can see that this is a non-homogeneous system. Clear? So, let us write it down. The question is 5x minus 7y equals 2, 7x minus 5y equals 3. Clear? Now we have this. What is this? As I just said, this is a non-homogeneous system of two linear equations in two unknowns x and y. Clear? That means here n is equal to 2. Whatever the role of n was being played over here in the theory that we had generated, over here n is being equal to 2. Clear? Now what are we supposed to do in order to solve this? Basically, we are asked to solve this system. That means we are asked to find out the solution of this system. That means we are asked to find out what all are the set of values of the unknowns over here x and y, which are simultaneously satisfying both the equations in the system and therefore are satisfying my entire system. I have to find those values of x and y which satisfy the first equation and the second equation, and therefore become the solution of first and the second equation, and therefore become the solution of the system. I have to find the value of x and the value of y. What is the first step in here? Step 1 is to write the given system in the matrix equation form. Just write it as what? Let me name this as, say, 1. I say that 1 in matrix form. Write it like this. This is Roman 1. So 1 in matrix form can be expressed as 1 in matrix form can be expressed as Ax equals B, where what is A? A is the coefficient matrix of which order? The order of matrix A is equals to n cross n, where first n is the number of equations, second n is the number of unknowns. Number of equations are 2, number of unknowns are 2. It's a 2 cross 2 matrix. In the first column is going to come the coefficients of the first variable x. In the second column will come the coefficients of the second variable y. So, coefficients of the first variable from the first equation, from the second equation. Coefficients of the next variable y from the first equation, from the second equation. This is your matrix A, my coefficient matrix. Your capital X is what? 2 cross 1 matrix made up with the unknowns, and B is again 2 cross 1 matrix made up with the right hand sides 2 and 3. Clearly, this is not a null matrix of order 2 cross 1, and therefore the system is non-homogeneous. A is this, X is this, B is this. If you compute Ax equals B, eventually you are going to get this system itself. We have seen that. So, this is another way of writing this system itself, and therefore finding solution of this system or finding solution of this matrix equation is exactly the same. That is what we have boiled it down to. Solving this system is same as solving this matrix equation, for which particular n cross 1 matrix known as X, if I plug it in over here, I get Ax equals B. Because A is known to me, B is known to me, what is that n cross 1 matrix, which if I put over here, I actually get this equation, matrix equation being satisfied, that if I multiply A with X, I am eventually getting B. What is that matrix X? So, it is this unknown column vector or column matrix of order 2 cross 1 which is what we have to find, so that when I plug it in over here, I actually get this matrix equation satisfied, right? That is my aim, and this eventually is going to give me the solution of this system itself. What is the next step? After this step 1, what is the next step once we have written it in the matrix form? Let's revisit. After you have written it in the matrix form, you eventually are now going to talk about the determinant of A. So let's talk about the determinant of A in step 2. In step 2, we will be talking about determinant of A. A is a 2 cross 2 matrix, it is a square matrix, so talking about its determinant is a valid point. Determinant of A is equal to determinant of 5 minus 7, 7 minus 5. Product of diagonals minus product of off diagonals. This is minus 25 plus 49, which gives you 24. If the determinant is not equal to 0, A is non-singular. If determinant is 0, A is singular. Here I am getting determinant is 24, which is not equal to 0. This implies A is non-singular. If A comes out to be non-singular, that means this system has a unique solution given by this. It is this particular capital X, which if I plug it in over here, I will get this matrix equation being satisfied. So let's write it down by our observation. This we already know. Let me write this question over here. This is 4x minus 2y equals 3. Let's write it downside. 4x minus 2y equals 3 and 6x minus 3y equals 5. So in here, coming back to our question, we have A is non-singular, right? So therefore, step 3, Ax equals B has a unique solution. It has a unique solution given by capital X equals A inverse B, where what is A inverse? How do we compute A inverse? We have seen in the very property that we did related to adjoint that A is non-singular if and only if A is invertible, and in that case A's inverse comes out to be equal to what? Because determinant of A is not equal to 0, therefore we compute A inverse like what? This is the scalar, because determinant of A is not equal to 0, and we take scalar multiple times adjoint of matrix A. So let's compute A inverse B. Already we have, then we are going to have capital X, which is going to give me my unique solution in this case. So what is adjoint of A? I am talking about adjoint of this square matrix of order 2 cross 2. You all know, we have seen that whenever I am talking about adjoint of a square matrix of order 2 cross 2, actually it means transpose of the matrix of cofactors of all the elements of A. So actually adjoint of A is again a matrix of order 2 cross 2, fine, which is obtained when you take the transpose of which matrix? At the 1/1th place its cofactor of 1/1th element, 1/2th place is cofactor of 1/2th element, 2/1th place cofactor of 2/1th element, 2/2th place cofactor of the 2/2th element. When you take the transpose of this matrix, what you get eventually is the adjoint of A. So what is this matrix? This matrix in shortcut we know is obtained by interchanging the diagonal elements and changing the signs of the off diagonal elements. When you interchange the diagonal elements, these are your diagonal elements. 1/1th becomes 2/2th and 2/2th becomes 1/1th. So you get minus 5 here and 5 here. And when I am talking about the off diagonal elements, I eventually magnitude wise keep them the same. I just change the sign. This becomes 7, this becomes minus 7. So you change the diagonal elements, interchange the diagonal elements, and you change the signs of the off diagonal elements. This is your adjoint of A. Obviously 1/24, because 24 is determinant of A. So 1/24 is the scalar times adjoint of A is actually what happens when a scalar is multiplied by a matrix. That scalar gets multiplied by every element of the matrix. So 1/24 gets multiplied with this matrix, so you eventually get minus 5/24, 7/24, minus 7/24, 5/24. Now you need to consider what? You know that capital X is given by 1 by 24 adjoint of A into B. So this is equal to 1 by 24. Adjoint of A is minus 5, 7, minus 7, 5, and B is what? What is my matrix B? B is equal to 2, 3. Now, this you can see this is a 2 cross 2 matrix and this is 2 cross 1. So, eventually in the answer of multiplying these two, you are going to get 2 cross 1 matrix, right? The first entry will be 2 1th or 1 1th and next will be 2 1th. 1 1th will be first row from here, first column from here, both get multiplied. Minus 10 plus 21. Minus 10 plus 21 gives you 11 and here you get minus 14 plus 15 gives you 1. 1 1th entry was obtained by multiplying first row with this column. 2 1th entry was obtained by multiplying second row with this column. And eventually what have you got? When a scalar gets multiplied by a matrix, that scalar gets multiplied with every element of the matrix. 11 by 24, 1 by 24. So capital X is coming out to be a matrix of order 2 cross 1, right? Capital X is coming to be a matrix of order 2 cross 1 with certain values, okay, with certain values. So we have capital X is 11 by 24, 1 by 24. This is that capital X which is satisfying Ax equals B with our given A and given B. Capital X was what? This. Two matrices of same order are equal when the corresponding elements are same. This implies X is 11 by 24 and Y is 1 by 24. It is this value of X and Y, the set of values of the unknown variables X and Y, which when I plug in over here and over here, both these equations will get satisfied. In fact, this is the only set of values of the unknowns which is going to satisfy both the equations. There is no other value of X and Y which if you plug over here apart from this, which is going to satisfy both these equations simultaneously and hence will become the solution of the system. There is only one such pair of values of X and Y. Okay, that means there is exactly one solution, unique solution to this given system. Okay, this is how you tackle with those systems of non-homogeneous linear equations in which the number of equations is same as number of unknowns, wherein the determinant of the coefficient matrix is non-zero. But if I take this next question that we have, let's consider this. What does it say? It is saying 4x minus 2y equals 3. The question is again to solve 4x minus 2y equals 3 and 6x minus 3y equals 5. Again you can very easily see that it is a non-homogeneous system of two linear equations in two unknowns. It is non-homogeneous system of two linear equations in two unknowns. Okay. The next step, the moment you have a full-fledged expanded system with you, the next step is what? The next step is to convert it into matrix equation form, right? How do you convert it in matrix form? Ax equals B, where what is A? What is A? A is the coefficient matrix. You know that there are two linear equations and there are two unknowns, so this will be a matrix of order 2 cross 2. Clear? The moment I know this is a matrix of order 2 cross 2, I know that in the first column will lie the coefficients of the first unknown x from the first equation and from the second equation here, and in the second column will lie the coefficients of the next unknown, which is y, in the order that here will be the coefficient of y from the first equation, here will be coefficient of y from the second equation. So therefore I have 4 6 minus 2 minus 3. Okay. Now in here, the moment I have A, I know X will be what? It will be a 2 cross 1 matrix made up with the unknowns, and B will be again 2 cross 1 matrix made up with the right hand sides. So it is 3 and 5. you know that I can write this particular system as Ax equals b with this A, this x and this b that I have written on the board. So in here, if you see carefully, the next step was what? The next step was eventually to compute the determinant of A. When I talk about determinant of A, what does this come out to be? Determinant of A is nothing but 4 minus 2, 6 minus 3. Product of diagonals minus product of off diagonals. This is equals to minus 12 plus 12 and that is 0. We have got a 0. We are not in this case anymore. We have reached this case when the determinant is 0, A is a singular matrix. So I can declare that this implies A is a singular matrix. A is a singular matrix. And when A has become a singular matrix, what is the next step? I am right now confused between two conclusions. Either the nature of solution is that the system has no solution, or the nature of solution is that it has infinitely many solutions. In order to distinguish between the two, actually which one is prevailing in this scenario for this given system, I will have to talk about adjoint of A. Let us compute adjoint of A. I know that adjoint of A for a 2 cross 2 matrix is again a 2 cross 2 matrix which is computed how? Well, you just interchange the diagonal entries of A and you change the signs of the non-diagonal entries of A and you get the adjoint of A. So, change the diagonal entries, this becomes minus 3 and this becomes 4, and change the signs, so this becomes minus 6 and this becomes 2. This is your adjoint. When you compute adjoint of A into B, this turns out to be minus 3, 2, minus 6, 4. Multiplied by matrix B, B is 3 and 5. You can see this is 2 cross 2, this is 2 cross 1, so eventually your answer is going to be 2 cross 1. It will have 1 1th entry and it will have 2 1th entry. 1 1th entry will be obtained when you multiply first row here and first column here. Minus 9 plus 10. Minus 9 plus 10 gives you 1. And when 2 1th entry is obtained, when second row is multiplied here with this column, minus 18 plus 20. Minus 18 plus 20 gives you 2. Clearly, adjoint of A into B is not coming out to be equal to null matrix of order 2 cross 1. If adjoint of A into B does not come out to be equal to null matrix of order n cross 1, you declare that there is no solution. And therefore, I say that system Ax equals B has no solution. It is inconsistent. It is an inconsistent system. That's how, just follow the lines which have been described over here. They are actually working as what? They are actually working as clear algorithm to give you the exact lines over which you have to just walk and conclude accordingly. Find whatever is the demand, just compute that and then conclude accordingly. So, quickly revisit this particular algorithm and the two questions that we have done. We are then going to move ahead and do another case related to this demonstration. Let us now talk about another question which is going to demonstrate another phase and picture of such a case. Look at this question. Here I am given 3 linear equations and 3 unknowns. It is a non-homogeneous system in here. How do I tackle this? Here n equals 3. I first of all write my matrix A, 3 cross 3 matrix. The first column is coefficient of x 2, 3, 4. Second column is coefficient of y minus 1, 2, 5. Third column is coefficient of z 3, minus 1, minus 5. It is a 3 cross 3 matrix. This is my A. And you have x as x, y, z, and you have b as 5, 7, 9. 5, 7 and 9. Now in here I am able to write it as Ax equals b. Okay. Next step, determinant of A. Now when you are going to compute determinant of A, 2 minus 1, 3, 3, 2 minus 1, 4, 5 minus 5. you will be able to see that if you expand it along row 1 or row 2 or row 3 or column 1 or column 2 or column 3, this is eventually going to come out to be 0. You can very easily compute this. We've done a lot of this practice. Determinant of A is 0. We move on to this category when the determinant is 0. Now my given system of 3 equations and 3 unknowns, which is non-homogeneous, is either having no solution or is having infinitely many solutions. There is a big question. In this case it will become inconsistent, in this case it will become consistent. So it's a big difference. So what is the conclusion, this or this? For that we have to compute the matrix adjoint of A. For this particular 3 cross 3 matrix, adjoint of A is what? Adjoint of A is transpose of the matrix of cofactors of A. Right? Let's quickly compute the cofactor. You know that cofactor of ijth element is -1 to the power I plus j minor of the ijth element. What will be the cofactor of? So we will be first writing the cofactor matrix and then we will be taking its transpose. Okay. So what is the cofactor of this element? This is 1/1th element, -1 to the power 1 plus 1 is 2, so it is 1. Just calculate the minor, it is, remove the first row, first column, you have -10 plus 5, so it is -5. Next you have this is the 1/2th element, -1 to the power 1 plus 2 is -1, so negative will be coming and being multiplied with its minor. First row delete, second column delete, you delete the first row and second column. What you get is -15 plus 4, which is -11, but minus will be multiplied, so it will become 11. Then you have 1/3th element, -1 to the power 1 plus 3 is 1, so nothing will be multiplied to the minor of 3. Delete the first row, third column, you have 15 minus 8, which is 7. Then you have this 3, this is the 2/1th element, -1 to the power 2 plus 1 is 3. -1 to the power 3 is -1, so minus will be multiplied by its minor. Delete the second row and first column, you have 5 minus 15. This is 5 minus 15, which is -10, multiplied by -1, this gives you 10. Then you have this element, this is the 2/2th element, -1 to the power 2 plus 2, -1 to the power 4 is 1. Just calculate the minor. Second row delete, second column delete, you have -10 minus 12, which is -22. After that you have this -1. This is the 2/3th element, -1 to the power 5 is -1. Now when you delete the second row and third column, you eventually get 10 plus 4, 14, with a -1 gives you -14. 3/1th element, -1 to the power 3 plus 1 is 1, so you get just the minor, this delete, you get 1 minus 6, which is -5. Then you have the 3/2th element, -1 to the power 5 is -1, delete the third row, second column, minus will be multiplied, you get -2, -9, -11, multiply -1, you get 11. And then you have this 3/3th element, -1 to the power 6 is 1, delete the third row, third column, you get 4 plus 3, 4 plus 3, which is 7. Okay. Now in here, the moment you have got this, you can very easily calculate the transpose of this. This is -5, 11, 7, 10, -22, -14, -5, 11, 7. Okay. The moment adjoint of A is here with us, we are going to calculate adjoint of A into B. When you do that, with this matrix as your B matrix, when you do that, adjoint of A into B, the answer comes out to be this. You can easily compute this, and therefore now we are in this category. We know that there are infinitely many solutions. System has infinitely many solutions. How to compute these infinitely many solutions? There is this trick. Out of the 3 variables that you have, take any one variable as a constant k. Now your system is going to be just involving 2 variables x and y. Out of the system of 3 equations, just pick up any 2 equations. You have 2x minus y equals 5 minus 3k, because I have replaced z by k. Okay, and next equation I am picking up the next one, 3x plus 2y equals 7 plus k. Out of the 3 unknowns, replace one unknown by k, take it to the right hand side so that you have just 2 variables x and y. I have replaced z by k. Out of the 3 equations, pick up any 2 equations, I have done that, right? Therefore, now it is 2 equations in 2 unknowns. Eventually, you need to calculate the same thing. Again, my matrix A will be evaluated 2, 3, minus 1, 2. Determinant of A will be given as 4 plus 3, 7, which is not equal to 0. The moment determinant of A is not equal to 0, therefore, capital X equals A inverse B is the solution. What is A inverse? I can calculate very easily A inverse. A inverse is 1 by 7 into adjoint of A. Adjoint of A, how do you get the adjoint of A of a 2 cross 2 matrix? Interchange the diagonal elements, change the sign of the off diagonal elements. So, A inverse and A inverse into B, if you evaluate directly, B is what? This 5 minus 3k 7 plus k. 5 minus 3k 7 plus k. Are you understanding? 5 minus 3k 7 plus k. Let me just remove this. Okay. Now, when you eventually calculate A inverse B, this comes out to be what? 10 minus 6k plus 7 plus k, and the next element would be minus 15 plus 9k plus 14 plus 2k. Okay. So, A inverse B is what? 10 plus 7 is 17, minus 6k plus k is minus 5k, and here it is minus 15 plus 14 is minus 1, 9k plus 2k is 11k, and you have 1 upon 7. So, this upon 7, this upon 7. A inverse B is equals to capital X, which is x and y. So, basically you are getting x equals 17 minus 5k by 7, y is equals to 11k minus 1 by 7, and z is equals to k. This value of x and y, when you plug it in the third equation with replacing z by k, you eventually are going to get that this equation is being satisfied. You won't believe that this x, y, z is going to satisfy the third equation, and therefore I get that this particular thing is a solution of the given system. For different values of k, for z equals different values of k, you will get different values of x and y, and therefore suppose k1 you have put. So, z equals k1, y equals 11 k1 minus 1 upon 7, x equals 17 minus 5 k1 upon 7 happens to be one set of values of the unknowns which is happening to be solution of the system. You change the value of k, you are going to get different value of x and y. So, for that value of k, x, y and z is going to give you another set of values of the unknown which is going to satisfy the system. So, different values of k is actually giving you different set of values of the unknowns happening to be its solution. How many values of k can you give? There are infinitely many real numbers. You can give infinitely many values of k, and therefore you are going to get infinitely many solutions of this system, and this is what the solution looks like. There is an unknown present in which you can plug in any value, correspondingly find out the rest 2 values of the unknowns and declare each set as one solution. So, this is the respective solution of the system. Is it clear? So, we witnessed all the 3 categories when the determinant was not equal to 0 with this not equal to 0, and equal to 0 with this equal to 0. Revise this very nicely. I will see you in the next lecture. Thank you.